Momentum of the ball, let us say, is 100 unit. When it hits me, all of a sudden it becomes 0. So the change in momentum has happened very fast. If the time interval selected is very small, that means momentum of the body is p, some force is acting on it. We take a very small time, very small time, 0.00000000001 second. Hello students, this is our second lecture in this series of NCERT physics. We are studying Newton's laws of motion, and in the last session we basically focused on first law of motion. Today we will understand Newton's second law of motion. Newton's first law of motion is basically a special case of second law of motion. In Newton's first law of motion, we talk about the situation when force on a given body is 0. But the second law of motion talks about a more general situation when there is some force acting on a body, right? So, Newton's second law of motion originally was stated using a new physical quantity which is known as momentum. So, let us first talk about what exactly is momentum. Momentum of a body is defined as product of its mass and velocity. Here velocity is a vector quantity, momentum is also a vector quantity. Momentum is mass times velocity. If you have a body of mass m traveling in any direction with velocity v, then we say that momentum of this object is m into v in this direction, in the direction of velocity. Momentum vector is always directed in the direction of velocity vector. If it is a 2 kg mass traveling at a velocity of 10 meter per second, then momentum of this body is 2 kg into 10 meter per second, which makes it 20 kg meter per second. So, unit of momentum is kg meter per second. Kilogram is used to measure mass and velocity is measured in meter per second. So, unit of vector is unit of momentum is kilogram meter per second, and important, it is in the direction of velocity vector. Now, the NCERT book tries to give you a feel for momentum. There are long passages written to make you understand what exactly this quantity is all about. Why do we need a quantity like momentum? I have summarized it in a phrase that momentum is nothing but it is measure of quantity of motion a body is having. Quantity of motion, it is a subjective thing that I would say, but we are trying to make it objective. We are trying to quantify the quantity of motion that a body is having. You all understand that a small bullet which is traveling at very high speed, if it hits our body, it causes lot of damage, isn't it? Even it can cause fatality. In fact, one may die if the bullet hits some important part of your body. Now, the bullet is not having a large mass, but it is having a very high velocity. So, velocity is high, though the mass is not very large, but velocity is very high. So, this quantity m into v is substantial, it is significantly large. Momentum of the bullet, that the quantity of motion that bullet is having is high, just because it has got very high velocity. At the same time, if a truck is moving at very slow speed and if it hits an object, it can again cause a lot of damage. Though the velocity is very small in case of truck, but the mass of the truck is very high, and therefore, this product mass into velocity, this is very high. We say that quantity of motion in that truck is very high. So, in nutshell, if a moving body hits something and causes lot of damage, then you can say that it is having a huge quantity of motion. And that quantity of motion is basically measured by product of two things: mass of the moving body and the velocity of the moving body. Think of a bullet which is moving very slowly. Will it hurt you when it hits you? Most probably no. It is not going to hurt you because the mass is small, and if the velocity also happens to be small, in that case the overall quantity of motion, that is momentum, is very small, and the bullet may not cause a lot of harm when it hits you. But similarly, if you think that because a truck is also having a small velocity, if it hits me, it will not cause lot of damage, then you are wrong, because though the velocity is small, but the mass is very high, and therefore the overall quantity of motion is very significant, and if it hits you, it is going to cause a lot of damage. So you can see that the amount of motion, the quantity of motion that a body is carrying is appropriately defined as product of mass and velocity. This quantity has been termed as momentum in physics. Now, the book says that momentum changes only when there is an external force. Momentum of a body will change only when some external force acts on the body. In absence of any external force, momentum of a body will never change. Momentum can change if velocity changes. Assuming that mass of the body is fixed for some time, let us assume that mass of the body is fixed. So momentum can change only when velocity changes. Now velocity is a vector quantity. It can change in two ways. There may be change in magnitude of velocity. If the speed becomes 15 meter per second from 10, then the velocity has increased, momentum has increased. But it may happen that magnitude of velocity, that is speed, is not changing, but the direction of motion is changing. If this body is moving with a velocity of 10 meter per second in this direction, and after some time I find that the same body is moving with a velocity of 10 meter per second in some other direction, then has the velocity changed? Answer is yes. It is a vector quantity. If the direction has changed, the velocity has changed. And if velocity has changed, we will have to admit, we will have to say that momentum of the body has changed. So this statement basically tells you that for a body of fixed mass, if we are imagining a body of fixed mass, then its momentum will change only when there is an external force. Okay. Momentum changes means either the speed changes, magnitude of velocity changes, or the direction of velocity changes, or both changes. So velocity changes means its magnitude changes, its direction changes, or both of them change. When that happens, then only momentum will change. And for this to happen, some external force is must. In absence of an external force, there is no question of change in momentum of a body. That is what is being said here. Later on, we will study somewhere that there may be systems which have variable mass, like rocket. When a rocket moves through space, its fuel burns and it is thrown out in form of exhaust gases. So the mass of rocket is continuously decreasing. So in that case also, the momentum of the rocket is changing. But that is some very special case, a bit difficult at this moment to understand. And if required, we will take up that topic later on. Let us move on from here. Now the book talks about how is rate of change of momentum and force related. This is a beautiful book, I would say, NCERT book. It first develops the concept. It tells you why do we sense a relationship between rate of change of momentum and force. It gives you examples to show that rate of change of momentum and force are related to one another. I am not talking about momentum and force. I am saying rate of change of momentum. The greater the rate of change of momentum, greater is the force acting on the body. In the earlier statement, we said that momentum changes only when there is an external force, and if the external force is very high, then momentum changes at very rapid rate, very fast rate. If the external force is small, then momentum of the body changes at smaller pace, smaller rate. Here the rate of change of momentum, this phrase means rate of change of momentum with respect to time, right? Rate of change of momentum with respect to time is high when force is high. Rate of change of momentum is small when force is small. There are many such examples to illustrate this. Okay. Suppose again, think of a moving car. A car is moving with some velocity, and if you gently apply brake, if you press the brake pedal lightly, softly, so that small friction acts on the tires, the speed of car will decrease, the velocity will decrease, but at a gradual pace. When you apply the brake softly, the velocity of car will decrease, but at a gradual rate, a small rate. The velocity will ultimately become 0, but it will decrease slowly. Momentum of the car, mass is not changing of course for the car, only velocity is changing. So, momentum of the car is decreasing gradually when the external force, the friction force acting on the tire is small. When the external force, that is the friction force acting on the car tires is small, the momentum of the car changes gradually. But what happens when you apply hard brakes? When you press the brake pedal a little bit harder, a big friction force acts on the car. And when the force is high, the friction force, the external force is high, the momentum changes very quickly. The car quickly comes to a halt. The velocity of the car decreases very fast. So, the momentum changes very quickly if the external force is high, isn't it? This is something that all of us must have experienced. If you are a cricket player, you do experience it every day. Even if you haven't played cricket, you must have played with some other ball in some other form, some other game. So, all of us have experienced this, that if a ball is coming at great speed towards us and we try to hold it at a fixed position like this, if I am trying to catch it like this, then I may get hurt actually. If the ball just comes into my palm and I hold it there, it may hurt. Why? Because what I am trying to do is, I am trying to abruptly change the momentum of the ball. This ball is having some momentum, and what I am trying is, I am trying to make its momentum 0 in a very small interval of time here only. Just instantaneously I want to make its momentum 0. Momentum of the ball, let us say, is 100 unit. When it hits me, all of a sudden it becomes 0. So, the change in momentum has happened very fast. This can happen only when there is a large force involved. That means my palm has to apply a large force on the ball, and this hurts. Rather than doing this, what a player does is somewhat like this. If a ball is coming towards me, I catch it here, and I bring my palms back, and I finally complete the catch somewhere here. I don't try to hold the ball here only. Just holding it here and not allowing it to move will imply that there is a large force that I have to apply on the ball. But if I prolong the duration for which the ball is in contact with my hand, I prolong the duration during which the momentum of the ball is brought to 0, then the force involved becomes smaller. I am not hurt if I catch the ball here and now I finish the catch. Now I completely hold it. So, what I am doing is, I am not trying to make its momentum 0 abruptly. I am giving it some time, and now finally the momentum is 0. So, when I am allowing some time, the rate of change of momentum is not that high, it is small, and therefore, force applied by my palm on the ball is also small. So I hope all of you do understand this. If you apply same force for same time, it will cause same change in momentum for different bodies. What does it mean? Suppose this is a smaller block and this is a rather heavier block. If I apply some force on this block and I also apply equal force on this block, I apply equal force on both the blocks for same amount of time, then what I find is I apply this force for time t, I apply this force for time t, then what do I see? What do I see? I see that the change in momentum of both the blocks is same. Yeah. This is lighter block, so after time t I will find that it is moving at very high speed. This is heavier block, I will see that it is moving at much lower speed as compared to this block. I applied same force on both the blocks. This is heavier, this is lighter. After time t, I found that this block is traveling very fast. This is traveling at a much lower speed. So, the speed of this block has not changed that much. But what about momentum? I find that change in momentum of both the blocks is same. If small m is mass of this block, then its momentum is m into v. If capital M is mass of this block, then its momentum is capital M into u. What I observe is this mu, this mv is same as this mu. So, the change of momentum that has taken place in both the blocks is same, right? Though they will not have same speed at the end of interval t, but they will have same momentum at the end of interval t. Now, the rate of change of momentum and force, the relationship between rate of change of momentum and force is actually Newton's second law of motion, as we will state very shortly. But here we are in the last slide also we were talking about rate of change of momentum and the force. Here also we are talking about rate of change of momentum and the force. And I was already talking about this kind of example. If you tie a stone in a string and whirl it in a circle, what happens? Now, the velocity, magnitude of velocity of this stone may not change. The stone may go in circle with constant speed, but the direction of velocity is continuously changing if it is going in circle. So, momentum is a vector quantity. If velocity, direction of velocity is changing, it means direction of momentum is changing, which means momentum is changing. So, momentum can change only when there is some external force. In absence of any external force, this object cannot go in circle. Here, this string applies an external force on this object and causes it to move on a circle. If you cut this string, this object is going to fly on a straight line. It will not go in circular path because there is no external force which will cause its momentum to change. For moving in a circle, it is necessary that momentum of this object keeps changing because velocity direction is changing. Well, momentum direction is also changing. So, there is continuous change in momentum, and that can happen only when there is an external force. In absence of external force, we cannot expect the direction of motion of a body to change continuously. Okay. Now, we are in set position to write second law of motion. Newton's second law of motion says that rate of change of momentum of a body is directly proportional to the applied external force and takes place in the direction of the force. If you apply a force on a body, then its momentum begins to change. Rate of change of momentum of the body is directly proportional to the applied force. This is what Newton said. What is rate of change of momentum here? It is delta p by delta t. What does it mean? If a body has momentum p at some time t, you apply a force, its momentum changes. Now, its momentum has become p plus delta p. This symbol delta p, delta is used to denote change. When I write delta x, I am saying change in x. When I write delta t is nothing but change in time. This is a standard symbol. So at time t, momentum of a moving body is p. Because of some force applied to it, its momentum becomes p plus delta p at a time t plus delta t. So the time interval has changed by delta t. There is a small change in time delta t, and in that interval momentum has changed by delta p. So what is rate of change of momentum with respect to time? Delta p by delta t. When I write delta y by delta x, its meaning is average rate of change of y with respect to x. So delta p by delta t is average rate of change of momentum with respect to time. And Newton said that force is proportional to rate of change of momentum with respect to time. Now you can write it with a constant like this, perfectly fine. But if you take, try to understand, if you take a large time interval, if delta t is very large, then this is actually average force, isn't it? Because rate of change of momentum may not remain constant over a long period of time. So this kind of calculation, change in momentum divided by time, this gives you the average force. If you want instantaneous force, if you want rate of change of momentum with respect to time at a particular instant, then what we should do? We should make this time interval extremely small. I hope all of you know that delta y by delta x, when delta x is made very small, delta x is tending to 0, this is written as dy by dx in mathematics. It is read as differentiation of y with respect to x. What does it mean actually? It is nothing but delta y, change in y, by change in x. This ratio when delta x is extremely small, very small. Similarly, if the time interval selected is very small, that means momentum of the body is p, some force is acting on it. We take a very small time, very small time, 0.00000000001 second, even smaller than that. In that duration, the momentum changes by small amount. That change in momentum by that time, which time? 0.0000001 second. This small change in momentum by this small time, this is the rate at which momentum is changing right now. So if I wish to write instantaneous force, force at an instant, at a moment, then I should write it as dp by dt. I am just omitting this part. Value of this ratio when delta t is tending to 0. Value of this ratio when delta t is tending to 0 is written as dp by dt. It is read as differentiation of p with respect to t. So force is some constant into rate of change of momentum with respect to time. dp by dt is rate of change of momentum with respect to time. Now, unit of force has been chosen in SI system. We have chosen the unit of force such that this proportionality constant becomes 1. Now it is proportionality constant and we are free to choose unit of our force. So unit of force has been chosen so that this proportionality constant becomes 1. That should not worry you much actually, and this equation is actually written as F is equal to dp by dt. What does this equation tell you? This equation tells you that if momentum of a body is changing, with time, then rate of change of momentum with respect to time is dp by dt, and this is the net external force acting on the body. If there is no force, if force is 0, then dp by dt is 0, which means momentum is not changing with time. dp by dt is 0 means p is constant, momentum is not changing with time. P will change only when this F is non-zero, there is some force. And moreover, students, this is actually a vector equation. So this equation is basically in vector form. It tells you that change in momentum happens in the direction of applied force. If a body is moving you apply a force in this direction, then in a very small interval of time, what do we find? We find that momentum of this body has changed in this direction only. Momentum is a vector, change in momentum is also a vector. What I am saying is, if force is applied in this direction, then change in momentum vector is also in that direction only. So, change in momentum happens in the direction of applied force. Here it is written. Okay. So, this is Newton's second law of motion. Let me put it in another form which is more useful. Now, I am not writing the vector sign, though it is force is a vector, momentum is a vector. For simplicity, I am not writing vector sign here. Now, please take a note that if a body of mass m is moving with some velocity v, then its momentum is, okay, I will not write vector sign, so sorry. If a body of mass m is moving with velocity v, then momentum can be written as m into v. And if we assume that mass of the body is constant, that means what I am going to do now is not valid for a system like a rocket. Okay, it is valid for some moving object, mass of which is not changing with time. So, if mass is not changing, that means mass is fixed, it is a constant. This mass can be kept out of the differentiation sign, and this differentiation becomes like this. Force is equal to mass times dv by dt. Now, all of you know that rate of change of velocity with respect to time. What is this? This is rate of change of velocity with respect to time. What is dy by dx? It is rate of change of y with respect to x. So, dv by dt is rate of change of velocity with respect to time, and rate of change of velocity with respect to time is known as acceleration. Therefore, what do we get? F is equal to m into a. What do we get? F is equal to m into a. But this is valid only when we are talking about a system which has got constant mass. Because Newton's second law says that rate of change of momentum is equal to net external force, and now if you replace momentum by mv and assume that m is constant, you are getting F is equal to ma. So, F is equal to ma is an equation which is equivalent to this. These two are same equations, provided mass of your system is not changing, mass is constant. So, in this particular chapter, we will be mostly dealing with this equation. We will be learning the application of this equation. Okay. Let us have couple of finer points about this law, which has been given in your book, and you must take a note of that. The second law of motion is a vector law. It is equivalent to 3 equations, one for each component of vector. Now, this second law of motion, which I have now written in this form, this is a vector equation, right? And actually, you can write it in components. This is vector expression simply means a set of 3 equations. Yes. वेक्टर नहीं होता तो कितना मुश्किल होता लिखना, ये आप सोच के देखिए. Because we have studied vector, we understand vector, we need not write these 3 equations, we simply write it like this. But actually this equation means these 3 equations. What is the first equation telling you? First equation says that the x component of net external force acting on a body. If there is a body of mass m and there are various forces acting on it, let us say, right? We have to find the x component of resultant force in this direction. We have to find x component, component of all the forces in this direction and add them. You can do that way, or you can find the resultant force and take its x component. Both will give you same result. So, the total force acting in this direction is Fx. this force is equal to mass times x component of acceleration. Because of all these forces, the body may actually be accelerated in this direction, It may happen that body is accelerated in this direction, right? But we have to take x component of this acceleration. We have to take x component of this acceleration. X component of acceleration into mass is actually equal to x component of force. What I am saying again, there are many forces. We have to find net force in x direction. The body may be accelerated in this particular direction. We have to take the x component of acceleration. So, x component of acceleration is basically x component of force divided by mass of the body. Similarly, y component of acceleration is force in y direction divided by mass of the body, and similarly z component of acceleration is obtained by z component of force divided by mass of the body. We will learn the applications through examples. Component of velocity normal to the force remains unchanged. Remember, component of velocity normal to the force remains unchanged. If a body is moving and suppose it is moving in this direction, and a force is acting on this body in this direction. So, the velocity can be broken into two components, one in the direction of velocity, one in the direction of force, and the other perpendicular to force. This velocity, we can take two components of velocity, one in the direction of applied force and the other one perpendicular to the force. This statement says that if a force is acting in this direction, then component of velocity in this direction will never change. In simple language, if a body is experiencing force in x direction, then its y component of velocity is not going to change. A simple example is projectile motion. When you throw a ball in air, what happens? Force acting on this body is always vertically downward, There is no force in horizontal direction, and that is the reason that x component of velocity remains constant. You must all have studied that x component of velocity, horizontal component of velocity in projectile motion is fixed. It does not change because there is no force in that direction. Force is always perpendicular or vertical direction. Force is always in vertical direction, and therefore horizontal velocity never changes, right? Another important aspect that we need to take note of is, in this equation F is equal to ma, no internal forces should be taken here. For example, motion of a car. When we are trying to calculate the acceleration of the car, we need not worry about how much force the engine is exerting on the other body parts of the car. That is none of our business to take into account those forces. Only thing that matters is external force. Only thing that matters is friction force applied by the road on the tires of the car. So, in this equation, F is total external force. If there are number of external forces acting on a body, vector sum of all those forces is mass times acceleration of the body. And acceleration means what? Later on we will realize it in a much better way. Acceleration is actually acceleration of center of mass of the body. Whatever be the shape and size of the body, if the total external force acting on the body is F, ये force कहाँ लग रहा है ये important नहीं है, जितने भी external forces हैं उनका vector sum है F. Then center of mass is a special point in a body about which we will learn later on. This particular point, center of mass, moves with acceleration A, and acceleration of center of mass is given by this force. For example, look at this pen. When I throw this pen in air, it performs a very complicated motion, isn't it? But when it is in air, only one force is acting on this pen. And that is weight force, mg, in vertically downward direction. So, net external force is mg. Though this pen is moving in a very peculiar manner, very complicated manner, but I am confident about one thing: total external force is mg, force is mg, that is equal to ma, which means A is equal to g. What is A here? A is acceleration of center of mass of the pen. Is pen makes special point a center of mass. And acceleration of center of mass is certain that it is g. I am not sure about other points in the pen. But in this equation, if I know the external force, divide it by mass of the system, you get the acceleration of center of mass. So this should not worry you right now. A is the acceleration of the body, knowing this is fine right now, but later on we will understand this equation in a much better way. Though because it was written in the book, therefore I am trying to explain it to you. And this is very important. Acceleration here and now is determined by the force here and now, not by the history of motion of the particle. This is very important. I said this in last lecture also, I guess, that acceleration of a body can be changed instantaneously. If you want, suppose mass of this object is 1 kg, if you want to make its acceleration 10 meter per second square, just apply a force of 10 Newton. If you apply a force of 10 Newton and mass is 1 kg, the acceleration will immediately become 10. Velocity and displacement cannot be changed instantaneously. Without giving any time, I cannot make the velocity of this pen 0 to 10. I have to allow some time. Then only velocity will become 0 to 10. But acceleration can be changed instantaneously. I apply a 10 Newton force, acceleration becomes 10. I withdraw that force, I stop applying the force, acceleration immediately becomes 0. Acceleration immediately becomes 0. It has got nothing to do with the history of this object. This is an object, it is experiencing some force F, its acceleration is F by m. The moment I make this force 2F, immediately its acceleration will become 2F by m. If I stop applying the force, immediately its acceleration will become 0. So when I stop applying this force, the body may keep moving because it has got some velocity, but its acceleration will become 0. That is important. So acceleration is not decided by any previous history of the body. It can change immediately from value x to value I without any loss of time. There is one example that is given in your book. A bullet of mass 0.04 kg moving with a speed of 90 meter per second enters a heavy wooden block and is stopped after a distance of 60 centimeter. What is the average resistive force exerted by the block on the bullet? I think all of you can give it a try. If you want to give it a try, pause the video, think about the question, try to solve it on your own. This is what the question is telling you. There is a bullet of mass m 0.04 kg and it is moving with some speed of 90 meter per second. Okay, very good. It enters into a wooden block and it stops after traveling a distance of 60 centimeter. This bullet pierces through this block, moves through a distance of 60 centimeter and comes to rest. Here it comes to rest. Here the bullet is having this speed u, but after traveling through 60 centimeter, it comes to rest. What is the average resistive force exerted by the block on the bullet? Okay, the way this question has been solved in your book is somewhat like this. First, we will try to find the retardation inside the block, retardation of the bullet inside the block using the equation of kinematics. This equation of kinematics can be used to find the retardation of the bullet as it moves from this point to this point. Again, look at this situation. Here the speed of bullet is 90 meter per second and here it is 0. So final velocity of the bullet is 0. Initial velocity means velocity here is 90. From here to here it was retarded. There was a resistive force and it was experiencing an acceleration in this direction. So let this be our positive direction. So acceleration is in negative direction. I am writing it as minus a, and the displacement is 0.6 meter, 60 centimeter converted into meter. So because I have written I have already taken into account that acceleration is in this direction. So, what A is just the magnitude of retardation. I am already saying that it is in this direction. So, what A is referring to is magnitude of acceleration. If I could recall it correctly, your book does not assign any direction to A, and therefore, they will get a negative value of A. I am not going to get a negative value of A because I have already said, I have already understood that acceleration is in this direction. Now, it makes no sense to get a negative value of A. I am already saying acceleration is in this direction. Plus and minus sign is always used to indicate direction. When I have already considered this acceleration to be negative, value of A is not going to be negative again. It will be a positive number. So, simplifying this, this gives me, oh, so sorry, 2 into 0.6. Am I right? So, you can do this calculation on your own, I think. Can you do it? Okay, I will do it for you. 90, first let us first get rid of this 0.6. Some of you might be finding it difficult. Let me do it. I have multiplied the numerator by 10 and I am also multiplying the denominator by 10. So, 0.6 becomes 6. Now, this cancels out. 6, 15 is 90, 15 into 6 is 90. So, this will become like this, and this 2 further cancels out, it becomes 75. So, 90 into 75 meter per second square is the value of acceleration. So, 0, 9 5 ja 45, 9 7 ja 63 and 4, 67 meter per second square. Please check if I have made some mistake or I think there is a, okay, I have the book in my hand. It says 6750 and I am getting 6740. Why? Am I wrong? 0, 9 5 ja 45. Yes, I am wrong. 9 5 ja 45, 9 7 ja 63 and then 4, 6750 is the right answer. 6750 meter per second square is the acceleration of the bullet. I hope all of you have understood how I calculated this. Now, when I know the acceleration, I also know the mass of the bullet. Therefore, the force that this wooden block is applying on the bullet in this direction, the average force is mass times this acceleration. This kind of average acceleration, because I am not sure if the acceleration was constant throughout. So, what I have calculated is an average acceleration. So, the average force is mass times acceleration. Now, here the mass of the bullet is 0.04 kg. So, I need not do any unit change, it is in kilogram, and 6750 meter per second square is the acceleration. So, I leave this to you, you can do it on your own. Here I am having the book and it says that answer is 270 Newton. Okay. I hope all of you have understood this. This is the manner in which it has been solved in your book. There could be other ways also, slight different use of equation of kinematics. In fact, this equation is derived from other two equations, V is equal to U plus AT and S is equal to UT plus half AT square. So, instead of using this equation, one can use those two equations also. Try to think about it for a moment, you will be able to realize this. There is another example, let me do it quickly. The motion of a particle of mass m is described by this equation, y is equal to ut plus half gt square, find the force acting on the particle. According to the language of the question, we get a feel that particle is moving on y axis and its y coordinate changes with time according to this equation. This equation basically tells you how the y coordinate of the particle is changing with time, right? If you do dy by dt, that means rate of change of y coordinate with respect to time, what do you get? You get velocity of the particle. A particle is traveling on y axis, its y coordinate is changing with time according to this equation. Find dy by dt, and this is nothing but, I hope you know this, u is a constant, it is placed outside the differentiation sign. Differentiation of t with respect to t is 1, and g by 2 is also a constant, and differentiation of t square with respect to t is 2t. So velocity of the particle is dependent on time. It is not independent of time. It is not constant. It is changing with time. We have got velocity. What about acceleration? Acceleration is obtained by dv by dt. Students, please pay attention. This is position coordinate. If particle is traveling on x-axis, तो यहाँ पे x होता. Particle is traveling on y-axis, y coordinate. dy by dt is velocity, and dv by dt is acceleration. dv by dt is acceleration. So this is a constant, and when there is an isolated constant, its differentiation is 0. Differentiation of u is 0. These two cancels out. G is a constant again, and differentiation of t with respect to t is 1. So you get g. So acceleration of the body is g. Acceleration of the body is equal to g. This is what we conclude, and it is constant. It does not depend on time. So find the force acting on the particle. So force acting on the particle is mass times acceleration, which is equal to mass times g, because we have found that value of acceleration is g. So what was there in the question? The question says that particle has mass m. We are supposed to write the force. So force is mass times acceleration, isn't it? So I know the mass, so I must be able to calculate acceleration. So from the given information, I should try to get the value of acceleration. How will I get acceleration? When y is given as a function of t, dy by dt is velocity. Now I get velocity as a function of t, dv by dt is acceleration, and I get the value of acceleration. So force is mass times acceleration, which is of course equal to mg. Students, just a minute. I think I'll take up the next part in next video, and after going through all the 3 laws, we will be in a better position to study the application of Newton's laws of motion. Most of the questions in NEET etc. exam, NEET and other exam is based on applications of Newton's laws of motion. So maybe we will take one more lecture to complete all the laws, to understand them in totality, and thereafter we will start applying these laws to various conditions, to various different types of questions which are asked in these competitive exams. I hope you enjoyed this session. Do like the video and try to share it with your friends. Help me in increasing my subscriber base. Thank you.